All right, next up are James and Isabel. James, I see you're ready. Can you hear us? Can you say something so we can test if we hear you?
Yes, can you hear me?
Yes, that's excellent.
Okay, awesome.
Turn up the volume and you can go ahead and share your screen.
Okay, oh, I think somebody's sharing right now, so I think you gotta do, like, let's try now. Yes, there we go. I'm gonna share my screen here. Let's go. Okay.
Which one? Here.
Okay, let me just. Can you see grading light up there, the first panel?
Yes.
Okay, Isabel, do you want to introduce us real quick?
Sure. Hey, everybody. It's really nice to meet you. I'm Zooming in from Rome today. James is in Canada. We're super excited to be here virtually, and we regret not being there in person, but it seems like it's been a fantastic day from what I hear. So congratulations on all of the fantastic work. So I'm just going to briefly introduce us, and then James will jump into the full length of the presentation because it's pretty brief. But I'm Isabel Ochoa. I'm an adjunct professor at the University of Waterloo School of Architecture, where James is also a researcher. This work, entitled Grading Light, started off as our graduate thesis, and graduate being master's thesis, and we've sort of it started about 2.5, 3 years ago now, and we've since continued to pursue the work after the end of our degree, I guess. So with that brief introduction, I'll just let James take it away.
Okay. So this work is kind of entitled, or this body of work, this research is entitled Grading Light. And let's see if I can move through slides here. So the outputs for this kind of body of research were a series of stoneware and porcelain screens that kind of varied in brightness and illumination based on how light was kind of obstructed, reflected, and transmitted across their kind of surfaces. So the prototypes were kind of developed at this full, like, one-to-one scale to kind of understand this relationship between sensory engagement and material properties. And we predominantly come from, an architectural background. So there's lots of kind of different kind of lanes in here, but I think we're very much focused on these kind of design objects very much from the start. So the research outputs kind of capitalize on the highly customized ways of altering light scattering behaviors, kind of not easily reproduced through any other forms of ceramic production processes. So the scope of this work focuses on kind of harnessing two types of 3D printed high-fired ceramic traits. The first one being in porcelain structures, light transmission and scattering through kind of a function of extrusion variability, and in stoneware structures, the kind of the direction of incident light through kind of porous multi-layered component sections, which you can kind of see here. So in the current kind of paradigm of these like ceramic material systems, sectional consistency kind of often conflicts with this desire for graded material performance. So liquid deposition modeling with clay. I lost a. Sorry. Oh, there it is. Sorry, I lost Zoom for a second. So liquid deposition modeling with clay allows for kind of these grading of complex sectional tessellations, otherwise kind of not possible through kind of alternative fabrication methods. So this research kind of develops a computational methodology for kind of grading brightness and light scattering effects via this kind of toolpath tessellation. So parametric modeling kind of enabled us to create these kind of rapid responses to these emergent toolpath deviations that occur during the clay's working properties in this kind of like just iteration and like this kind of process of working through these small iterations of clay structures. So the research kind of presented was conducted using two commercially available LDM printers, the Potterbot SLX1 and the Ludum V4. The Potterbot SLX1, it's a big scar printer, and it was used for most of our stoneware. It's got like a really massive cartridge, and it's quite a quick printer. And the Ludum V4 is a gantry type printer with the kind of, I'm sure you're all familiar with it, with the printer kind of head attached to the X armature. It's got that two-part system, an auger and a cartridge, a pressurized cartridge. And this one certainly sacrifices speed and kind of scale, but we use that for all our porcelain because it can print much thinner, it can print much more delicate structures. So the kind of plastic material behavior of clay, when harnessed by LDM, kind of represents this whole world of former languages, which we're really excited about. The striations left by the extruder are kind of inherent to all ceramic artifacts manufactured with this technology at lots of different scales, right? With concrete printing, with clay printing, all the way down to kind of these plastic printings and these polymer printings. So the tool path and resulting kind of tool mark of this digitally fabricated kind of ceramic artifact can operate at like such a wide range of scales, and how the manufacturer addresses this tool mark in the printing process kind of directly affects this typology of the 3D printed clay artifact. So kind of through this lens of examination, three categories of expression kind of emerge from our research in the broader field of printing with clay. So the first one is tool path as kind of a byproduct form definition, tool path as an expression of ornament, and then tool path as a kind of a function of performance. So these categories employ like a wide variety of digital and physical workflows, and they exist on this massive spectrum with like big room for overlap. But the one we're really focused on is kind of this third one. And this third one being kind of the tool path as like a functional performance. So in this category 3 here, tool path is a function of performance. The print layer deformation is both kind of ornamental and performative, and it takes on this kind of structural characteristics that are inherent to the clay behavior of clay, both ceramic and kind of working properties of clay. So category 3 takes shape in kind of like porous print structures, non-planar printing, and other methods that kind of obscure the continuity of the print layers through kind of like high degrees of deformation. And these are 2 projects that in our research were kind of very, like really got us going and thinking about this, this idea. It's non-clay wovens and spatial print trajectories. These 2 kind of like lattice work, 3D printed kind of clay structures, or not necessarily clay, but kind of LDM printed with kind of like LDM processes. So our light screens are categorized kind of by the number of print layers required to create an aperture. And an aperture is just essentially like an opening that we use to kind of control the direction or kind of brightness level of light. So although the kind of the formal expressions, the illumination, the plastic deformation, the structural stability differ substantially between all these different light screen typologies, the number of layers in a print pattern remains kind of this universally significant parameter for kind of determining form. So from that perspective, they're kind of categorized small, medium, large, and extra large. So the small typology consists of kind of non-porous geometries that rely on translucency of porcelain to diffuse light. So they're non-porous. And the medium, large, and extra large topologies rely on the plasticity of kind of stonewares and porcelain, actually low fire porcelains, to create open work structures that scatter light across kind of distinct sectional conditions. So getting into these, the final prototypes within each light screen kind of capitalize on both the clay's working properties and the ceramic performance characteristics. So if you can imagine, increased porosity and thin wall sections really does promote instability. Since none of these prototypes kind of in our research utilize any sort of formwork or structural support during wet processing, the tool paths were kind of very carefully considered to also prevent structural failure. So the prototypes really attempt to push the structural formation, the structural limitations and the material limitations, and harness this relationship between kind of light and ceramic surfaces. So getting into the specific kind of the specific lights we kind of sought to develop. We'll start with the S here, the smallest one. So brightness and light scattering in the small typology is kind of primarily regulated by porcelain thickness. So material thickness at a given location determines the amount of light transmission across the clay body. So graded light transmission is achieved by using kind of 2 different tooling operations that are almost overlaid on top of one another. You can see it here in these images. So there's extrusion variability, and then there's waves that expand and contract in amplitude to kind of change the sectional distribution of material. So the final S prototypes are a series of kind of pendants that illustrate this relationship between these 2 parameters. So both materials are attached to kind of a set of variable domains that control this material deposition and wave amplitude relative to the exact location on the prototype. While the variable extrusion does not kind of change across the series, so it's identical to each one of these pieces. Wave amplitude is kind of vertically graded from the top to the bottom across 6 pieces, which you can kind of see at the bottom there. When the waves expand, it's additional information that's deposited along the XY, resulting in kind of diminished brightness. So the first and last piece kind of represent this continuous vertical and minimum and maximum amplitude. The other ones represent this kind of gradient in between. in between. So the second one here is brightness. The second one here is the medium one, and brightness and light scattering in the medium typology are controlled by this kind of aperture size. So the apertures in the final M prototype are vertically graded. This vertical shift kind of creates three distinct conditions that form these horizontal bands across the light screen. And the top kind of tapers in to kind of crunch the printed pattern to kind of deform it and create a new geometry as well. So maximizing aperture size is probably the most significant contributor to plastic deformation and structural collapse in the M typology. Porosity, as the porosity increases, so does kind of the risk of deformations and the risk of structural collapse. So the surface to which the pattern is digitally mapped kind of acts as like this datum for us. And if you can imagine, the farther away we pull kind of material from that datum, or like the more asymmetrically we pull material from that datum, the harder it is to print, and instability is really aggravated by this. That's why a lot of these kind of still are portrayed as kind of symmetrical pieces. Because the focus was not necessarily this form finding, the focus was really on this embedded kind of function into the skin, like the kind of micro pattern here, the pattern at the scale of the single print layer. So the final M prototype, I move to this one here. The final M prototype, it kind of like sectionally shifts along its most kind of contoured area on the shade. So as a result, this piece actually does require physical intervention. So we typically with this piece, we torch it or heat gun it for around 5 minutes, halfway up the piece, to prevent essentially this thing from kind of collapsing in on itself. And so the heat gun essentially stiffens and reduces moisture in the clay during the printing process, which allows us to kind of essentially prevent what's happening here on screen. So the L prototype, the large, is kind of a two-part prototype here. So brightness in this large prototype is kind of controlled by aperture size as well, but it's a very different kind of operating aperture. It's a directional aperture. So the apertures in the L prototype are kind of vertically graded. So brightness and light scattering gradually increases towards the bottom of the screen, which you can kind of see here in the photos. The L prototype borrows from a lot of actually former elements from traditional lamps. So it has a two-part component. It has two kind of components, a housing and a shade, or like essentially a housing at the bottom and a shade on the top there. The shade is kind of vertically flipped 180 degrees about its printed orientation. So it's printed upside down to direct kind of these light apertures downwards. And the same pattern is applied to that housing, but at that point, it's just ornamental, the bottom there. So two very specific strategies were implemented in the kind of prototype to maximize aperture size while preventing structural failure, which is the negotiation among all these pieces is maximizing aperture size while preventing failure. So the first kind of implemented strategy was this kind of interlocking mechanism where the pattern actually kind of overlaps and interlocks with one another. You kind of see it here in these moments. And this minimizes the tendency for those patterns to kind of splay out. And the second is kind of creating this geometry that mitigates the tendency for the layers to buckle in on one another. So the conical form of the shade is like, it's a very nice aesthetic thing, but it really exacerbates its tendency to kind of splay out essentially. So there's a convex series of layers in between visible kind of concave series of layers. And essentially buckling is diverted to this convex layers, kind of deforming into flat surfaces, which you can see on this overlay here. So one overlay is essentially the print, the material toolpath, and the second is kind of where it essentially settles after printing. So the latter strategy in this kind of toolpath design also serves to direct incident light downwards and kind of eliminate any glare that you'd ever experience from the light source. Okay, so the final light prototype here is the large or extra large prototype, and brightness and light scattering in this extra large is kind of controlled by aperture size and also by extrusion variation. So it actually shares a lot of similarities between the porcelain, the small, that very first one. And it's kind of a combination of all of them. It's this weird kind of amalgamation of all those different kind of typologies we just went over, kind of put together. So the apertures in this kind of extra large prototype are vertically graded, and brightness and light scattering gradually kind of increase toward the bottom of the piece. Grading light conditions are achieved by using kind of two digital tooling operations. One of them is extrusion variability again. And the other one, which again is kind of expanding these wave apertures to essentially create kind of like moments for sag and moments to open this kind of skin. So extrusion variability is attached to kind of a variable domain that controls material deposition relative to any given location on the prototype. And when kind of extrusion increases, more material is being deposited, right? So at any given moment, if we can kind of control the extrusion variation over essentially over a void in the geometry, it kind of expels out and then creates kind of these really dramatic unsupported moments in this sag, resulting in this really kind of significant kind of deformation, controlled deformation. Greater extrusion really does result in higher degrees of print delamination, which kind of allows moments for light to escape this piece. So extrusion variability is probably the most significant contributor to plastic deformation in the XL prototype. The volume of clay deposited over this whole piece is reduced by 50% as it goes up the print. So since most materials distributed at the bottom of this piece, it's like super stable. It's like building a pyramid, essentially. It's hard to topple. These nonlinear kind of domains require a lot of these linear domains are really helpful because nonlinear domains require a lot of fine tuning to alter kind of light scattering behaviors while maintaining structural stabilities. And then the linear domain was also found to be kind of a much nicer gradient use of light over the whole piece. So these kind of these four prototypes presented took shape very late in our material studies. And these light screens were created as kind of a comprehensive representation. They weren't necessarily the end goal. They were just kind of a comprehensive representation of this methodology we've continued to work on. So this kind of process-based approach to material composition has kind of allowed us the opportunity to expand the scope of this research a lot into three projects really. I'm going to go over very, very briefly now. So the first one being Hive, which David mentioned. It's the ceramic kind of 3D printed installation developed at University of Waterloo with the team there, headed, of course, by David. And the second was a kind of a small course we taught on functionally graded performance in terracotta structures. And it was co-taught with Isabel, myself, David, and this kind of course taught kind of computational workflows and digitally crafting ceramics. So the course was taught with Architectural Association Visiting School last summer, and in association with Autodesk Technology Centers. And these two projects really allowed us to investigate two key questions, which we didn't necessarily get to answer in our research, in our thesis. How do we assess the kind of constructability of designing using kind of production workflows established in our research methodology? And what is the impact of kind of representation and simulation in the design and fabrication process of these 3D printed structures? So Hive allowed us to kind of test the structural limits of the material performance and the efficacy of our kind of design to production workflows at a really large scale. The stoneware units in Hive kind of form these apertures that selectively expand and contract to allow us to kind of visually make connections between it and create light passages almost. And we also learned a lot essentially about applying standard masonry kind of production to non-unitary bricks, which was quite an experience in and of itself. This is pictures of Isabel and I constructing essentially laying that prototype like you would a traditional masonry wall. And so, like I said, in August of last year, we also had the opportunity to co-teach a course to a bunch of students our working methodologies that was taught remotely as part of the Architectural Association Visiting School program. This 2-week workshop asked students to kind of think about how to harness terracotta's working properties and ceramic traits using kind of a set of material computation tools that we gave to them. So the Autodesk team also helped us create this kind of clay simulator in Bifrost in preparation for the workshop. So we were able to take the students' toolpaths generated in Grasshopper and visualize them in Autodesk. And although this simulator was not able to kind of mimic the structural performance, because that would have just been such a heavy simulator, it was able, the one important thing to us was essentially feedback in real time, because there's no point in running an hour simulation if you can run a 20-minute print. To figure out for sure what you're looking at. So it was very important that this kind of happened in real time. So although the simulator was not able to kind of mimic structural performance, it could compute kind of these micro collisions, this thing we're really interested in, this embedded kind of function into the kind of almost skin of a piece. At this point, kind of harnessing the unique types of material performance in the students' perspective projects kind of took precedence over this adherence to any computational methods provided. So material computation kind of became a way for the students to take agency over their projects while they were in the process of learning to kind of adapt to this new design framework. And teaching became a very exciting part of this feedback loop on our production process of materialization, and really pushed us outside kind of these boundaries. And because each student wanted to apply this to a completely different kind of world. And it was really exciting to kind of follow those students into that world. So this picture right now is essentially a comparison of a render done, a real-time kind of render done with this tool, this Bifrost tool that Autodesk developed with us, and essentially its physical counterpart. And you can see it really does start to express those kind of, not necessarily like if this thing will print at all, this kind of these larger questions of structural failure, but this kind of, it starts to express kind of this micro scale of delamination and controlled deformation to create these very intense patterns that kind of get away from traditional 3D printed kind of tool markings. And finally, right now, we're kind of focusing on the commercial viability of printing. That's where we're at right now. So the culmination of a lot of this research and design is actually like a series of objects that are at on exhibition right now at the Canadian Clay and Glass Gallery in Waterloo, Ontario. And this is kind of part of a commercial venture for us that we're kind of looking now to test out the kind of the commercial viability of 3D printing products. So that's where we're at right now. I think that's everything.
Thank you so much for this remote presentation. Hope you heard the applause that you got.
I heard a little bit of it, yes.
I think if I use the phone now, I'll build a feedback loop. So if there's any question, I'm happy to pass this on to James and Isabel. If there's anything from you guys you would like to know. No question from the audience, but I do have a question. What you've shown is a rich experimentation and exploration of the geometric features and of the toolpath planning and everything. It seems super involved. Did you do any material mixture testing on top of this, or did you come up with a formulation that then you were good with to explore the geometry and everything?
So we were kind of reluctant. We were briefly kind of thinking about experimenting with, like, we talked to people essentially in the slip casting world, which is if we're ever going to change the kind of consistency or the kind of reaction of clay with moisture in the 3D printing process, it would kind of be additives used usually in traditional slip casting, not traditional, but kind of what's the word, in kind of industrial slip casting. And so there's lots of different kind of agents we were looking at. Ultimately, we only ever added, like, we would buy essentially specific clays, and we'd only ever really soften them by just adding water. We wouldn't add, like, there's lots of other kind of things people like to add. We never actually did that. We found that there's a couple of clays that worked well for us, and they're highly temperamental clays. They got like really wild because essentially we're printing everything in porcelain, and porcelain's like it's a very volatile clay to begin with. So we didn't want to necessarily kind of add to that. We didn't want to necessarily add to that, especially because a lot of these porcelains are there. So if you can imagine, they're low fire, high translucency porcelains, which do not, I guess, occur naturally. They're usually they're manufactured, and a lot of the porcelains we're using are what's the word? They're patented. So we actually don't even know what's in them. They've got, like, each one of them has like 3 or 4 patented ingredients that are not shared with the public because they're branded these like the low fire, high translucency. So in that respect, no, we're kind of like, we don't know what's in them already, so we don't know what, like, you know what I mean. We could take guesses as to what those kind of things were, but that's a world we want to get into, but we haven't really got into yet, mixing our own clay bodies.
All right, thank you so much. I have a follow-up question on this, and then there's one from the audience. You showed the simulation of your material. How did you determine all the material properties that you need for it? The rheological parameters, which I assume you need, elastic properties and everything.
So it's that was really funny because Bifrost, we're working with the Autodesk team, and I think it's across the board here. Autodesk, like, they've got fluid simulators, they got solid particle simulators. Clay is neither, which is the problem, right? There's no good way to simulate clay, which is the kind of discussion we were having with the team. Like all their kind of frameworks for like fluid or particle simulation didn't come close to like kind of all these like viscoelastic properties, right? So what ultimately this simulator actually is, that's why it doesn't perform any sort of like structural variation. Essentially, what it is like it's a particle simulation with a ribbon. And essentially, like once the ribbon or once a particle kind of interacts with a different one, it locks in place. So as this thing simulates, it's locking the bottom structure in place. So it's not actually like what it is it's expressing deformation. And all that is essentially, it's like, if you can imagine, it's what we're simulating is essentially is a string it's a very sticky and very elastic string. And we worked with the team to essentially kind of move backwards. We sent them a bunch of our prints. So the best way is like the best thing we can do is simulate this string that kind of locks in place once it kind of starts interacting. And we sent them a bunch of our prints. We have got such a wide body of kind of like we've filmed all these. So what we did is we sent them all the film footage, all the photos, and they worked backwards essentially to kind of like they worked backwards to kind of match the elastic properties of specifically the terracotta we were working with. And then they gave us the parameters essentially, so we can kind of match it to the weight and stickiness and kind of thixotropic properties, the sag of a specific body. But all it does really well is essentially it shows you what you're about to print, but it doesn't actually to perform to perform structural analysis. You could do it, but if you can imagine, like the whole thing would kind of have to be constantly interacting with everything all at once. And that would take like this rendered in real time, which is beautiful, which is what we needed. Like you could pop it in and it looks like it takes 30 seconds to think about it, or not even, it takes 15 seconds. So that was the real thing. These students had only 2 weeks. We couldn't have them sitting and waiting for renders. So something that may or may not work.
Yeah. All right. Thank you. Then there was one question, Uli. All right. So the remark from the audience is that Uli suggests that you get in touch with someone at the University of Eindhoven. Juliet Beckering. Uli will email you that name.
I'm scrambling now for a pencil.
She is investigating similar things as you do with clay. She's doing that with concrete. She said you should get in touch. All right. With that, I would suggest we wrap up your presentation. Thanks again.
Well, thank you for having us.
Thanks for having us.